In this video, I would like to talk about integration by trigonometric substitution. And there are lots of different problems, and we could go deeper into this, but I really wanted to focus on the types that you might see on the AP exam. And I wanted to just point out for a couple of things. I guess, first of all, I did put down the two most common, inverse tangent, the derivative, and inverse sine, or arc sine and arc tangent. The other one, of course, the big one that's missing would be arc cosine. And the only difference with arc sine and arc cosine is arc cosine would be a -1. So it's just the opposite of arc sine. And what you're looking for when you start to get to this point in your kind of integration techniques is you're starting to look at things where all the other techniques have failed. For example, this first one up here, we've talked about substitution a lot, and you'd say, well, if I made u, it's almost always the denominator, if I made u 25 plus x squared, then of course the derivative would be 2x. I'd need an x, and I don't have one. So substitution, just straight substitution, will not work. So then the next method you start to think is, well, could I factor the denominator and use partial fractions? And of course you'll see here you cannot do that, because it's 25 plus x squared. So factoring, if you think back to Algebra 1, Algebra 2, it really is a method of finding zeros. This has no zeros because it will never touch the axis. So it's at that point where substitution and partial fractions doesn't work, where you go to this, using the inverse trig functions. This, to me, I guess the way to look at it is that because it's plus and x squared, I'm looking to use tangent, okay, or inverse tangent. So I guess first thing I would do is I always think of taking these constant multipliers and pulling them out front. Okay, so I put that 7 there. So now I've just got 1 over 25 plus x squared. And that really does look a lot like the inverse tangent. The big thing to kind of look for and aim for is to make it a 1 here, 1 plus, and we can deal with that x squared coefficient if there is one. But we really want to get that first number, that value, down to 1. So this, to get this to 1, I'm going to factor a 25 out. I'm going to kind of do my work right below it, and then we'll move off to the side. If I factor a 25 out, I've got 1 plus x squared over 25. Okay, kind of make sure you see what just happened there, that I took the 25 out of both. And of course, the easiest way to check is to say if I multiplied it back in, would I get this? And I certainly would. And now with this 25, it's a multiplier. I'm going to pull that out front. So let's rewrite this integral. We've got 7 over 25 times the integral of 1 over 1 plus, and before I write x squared over 25, I'm going to do just a little work here to make it something squared that equals x squared over 25. If I made this x over 5, and again, just kind of check yourself here, say, okay, yep, x squared, 5 squared. But what I just did was I now turned it into something that really looks like this inverse tangent. So now I'm going to use kind of the old-fashioned substitution. I'm going to say u is equal to x over 5, or 1/5 x. So the derivative is just 1/5. So if I multiplied both sides by 5, like this, like that, I'd have 5 du equals dx, and then I could do that substitution. So let's put our 7 over 25 times the integral. I'm going to leave just a little room for that constant that'll come out front, that 5. I got 1 over 1 plus u squared. Well, of course, 7 25ths times 5 is just going to be 7/5. And the antiderivative of what's inside there is inverse tangent of u plus c. I'll resubstitute back in. there we have it. Now I want to do another one, but again, let's just kind of track through what we just did. We spotted that our old methods weren't going to work because it was not, we couldn't use substitution, we couldn't use partial fractions. So we identified that it was very similar to inverse tangent. We kind of set to work making it inverse tangent. I factored the 25 out, so it's really important to have this number be 1. And then here, we did a little algebra to make it look more like inverse tangent. We said x over 5 squared is exactly this. And then we could use straight substitution. We said u is equal to x over 5, so the derivative was 1/5 dx. I put the 5 over, so we could just replace dx with a 5 du. So we had the 5 out front, and then we finished it off. Okay, this one. This looks very similar now to inverse sine. And let me just remind you that the only difference between the two, inverse sine, inverse cosine, is a negative. So let's do kind of the same thing. I'll put this work underneath. I want this leading number here, I want this to be 1 because it is 1 minus. Okay, so I'm going to factor a 49 out. So I'm going to have 1 minus 9 over 49 x squared, like that. Okay, now it is under a square root. Now square roots are can be distributed over addition, or I'm sorry, over multiplication and division. So really you can think about this like it's the square root of 49 times the square root of 1 minus 9 over 49 x squared. So I'm going to do that square root of 49. That's just 7. So again, notice it's in the denominator, and it's a constant, so I can now pull it out front, 1/7. I've got 1 over the square root of 1 minus, and let's make that same move. Let's say it's going to be something squared. That'll give us that 9/49 x squared. So let's say it's 3 over 7x. And now you'll see how similar it looks to that inverse sine. So let's use our substitution. U equals 3/7 x. So du is 3/7 dx. I keep forgetting my dx's here. Okay, so multiply both sides by 7/3, like that. So my integral becomes, I had that 1/7 already out. Now I've got a 7/3. 1 over the square root of 1 minus u squared. Okay, so it is 1/3 inverse sine. Ooh. And I'm gonna resubstitute just for the sake of space here. 3/7 x plus c. Probably the part that trips people up the most on this one, and you just have to be careful, is right here with, the fact that we factored out the 49, and then we could take the square root of 49 to be 7. And because, remember, it's in the denominator, so it's like pulling a 1/7 out front. And then, again, just straight substitution after that. Okay? All right, let's finish this one up. I'm going to just maybe move some of my work kind of out of my way. This one doesn't really look like it's lines up to a trig function, and certainly it looks like maybe you could do some factoring. You cannot. You can't do any factoring here because we have no numbers other than 1 and 17 that multiply to be 17, and certainly nothing that adds up then to 8. So what we're going to do with this, and again, this is something to just kind of spot, that we have a couple of methods for finding zeros when they do exist, but we can't factor. And the best method here to use is completing the square. So if you'll remember, completing the square really focuses on this, and we could just kind of deal with the constant as we need to. So I'm going to write below this, I've got x squared plus 8x plus blank, and we got plus 17 minus blank. Okay, so let me explain. We're going to complete the square, which I hope you remember how to do from pre-calculus and algebra 2. We're going to complete the square, but we can't just add something to the denominator without also subtracting off, this keeps that equality, right? We can't just suddenly add a number, but if we subtract it in the same, on the same line, this keeps it equal, so we're fine. Now, the way to complete the square, I hope you remember, is you take half of this value, so half of 8 is 4, and then you square it. So we're going to have a plus 16. That will complete this square, and then we're going to subtract off 16. And again, just make sure you see why we did that, that this right here is x squared plus 8x plus 17. We have not changed what the denominator is equal to. But what we have done is we've made it x plus 4 squared plus 1. Okay, let's put my integral up here with a little bit of reordering. 1 over, I'm going to put the 1 first, 1 plus x plus 4 squared. And now, look how much it looks like inverse tangent. So a little substitution. U equals x plus 4, du equals 1. We don't even need a multiplier. So this becomes the integral of 1 over 1 plus u squared, which of course is inverse tangent of u. And we resubstitute. It is the inverse tangent of x plus 4. So again, the spotting the need to do completing the squares may be a little tricky. I would look for things that look factorable, look like that would be our method. This certainly looked like something we were going to use partial fractions on, and the only problem is we couldn't factor it. So we're kind of at the same spot we were even on these other problems where it feels like we're kind of at the end of our methods. And let me be very clear, trig substitution should be your last resort. You should have already tried regular substitution and partial fractions. This is the last thing you want to try. But down here you'd say, well, okay, it looks like I should use partial fractions, but it's not factorable. So then you try to complete the square. That's kind of your next method. And just it worked out great because then it ended up with this plus 1, which was perfect right here, right? And then we could easily kind of fit it into our inverse tangent antiderivative.